This chapter is about voltage, also called potential difference, also called EMF, also sometimes just called electric potential. Now, unlike any course that you have been doing that involves voltages in circuits, we will mainly be talking about voltages just in space, in empty space, where there exists an electric field. So positive point charges are sources of electric fields. We've seen that already in the last chapter. And that field exists in that space, whether there's any particle to fill it or not. Now, associated with this electric field are what are called equipotential lines, equal voltage lines. And they are lines around which, if you take a charge and you move, you won't be doing any work. Okay, so these circles are called equipotential lines. And they are associated with numbers. You calculate the number using this formula that the voltage is KQ over R, R being the distance away from the charge. And so, for example, this line might be the 100-volt line, and this line might be the 50-volt line. And the lines are not equally spaced because it goes as 1 over R. So the 25-volt line may be out here and so on. And at infinity, when R equals infinity, the voltage is 0. Now, a good way to understand, well, let's do one more thing. If you have multiple charges in a region, they will all contribute to the voltage in the space around these charges. And if you want to know the voltage at any particular location, you simply need to know the distances from these charges. So if this was Q1, R1, Q2, R2, and Q3, R3, the voltage here would be K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. It's just the sum of the voltages from each individual charge, and it's a scalar. That's the beauty of this. These are just numbers, and they are negative. So this would be a negative number because it's a negative charge. So you do put negative numbers in. Now, a good way to talk about what happens with charges as they move around in electric fields is to imagine a parallel plate capacitor hooked up to a power source. And so this plate would be the positive plate. This plate would be the negative plate. And if this voltage, say, were 20 volts, the electric field is uniform and points from the positive plate to the negative plate. And associated with its electric field is a set of equipotential lines. So the 20-volt line would be up on the plate, 20 volts. And then the 10-volt line would be halfway between. And now this is a case where we do have, if we ground this and decide to make this 0, then we are dealing with 0 here, not at infinity. And this is 0. So notice how as you move in the direction of the electric field, the voltage gets smaller. So you're going from high to low voltage. So let's think about what happens if you put a little positive charge in here. This little positive charge is going to feel an electric force. And we know what that electric force is. It's QE. And that electric force is going to make this charge accelerate down towards the negative plate. And as it accelerates down, it gains kinetic energy and loses electric potential energy. So some of the formulae that are going to come up in this chapter are that the change in electric potential energy, now your textbook, I think, calls it U, is equal to Q delta V. So the change in potential energy depends on that little charge and then depends on the change in voltage. So this is very similar to gravity. If you have a mass close to the surface of the earth, there's a gravitational field. It feels a gravitational force, mg, and it will accelerate down, gaining kinetic and losing gravitational potential energy. So it's the same kind of idea. Now the difference between gravity and electricity is, so there exist negative charges too. You don't have negative masses, although that's a whole nother discussion. It is possible. So these negative charges, they will accelerate up. they will feel the electric force up. And so they fall up the voltage hill. And so as they move, as these negative charges move up, they will gain kinetic and lose potential energy. But the voltage lines here, they have nothing to do with these charges. The voltage lines are determined by this electric field, and they stay fixed. Whether the charges are accelerating up or down or whatever they're doing doesn't matter. Conservation of energy, you're going to need. And so if we pick 2 points in this electric field, A and B, and think about a little charge moving from A to B, energy is conserved. So the kinetic energy of that charge at A plus the potential energy at that charge at A must equal the kinetic energy at B plus the potential energy at B. So Q times charge times voltage is energy. And that's another thing that you're going to come across, this unit called the electron volt. EV is actually a unit of energy. E being the charge on the electron, 1.6 times 10 to the minus 19 coulombs times 1 volt. It's the energy that an electron gets being accelerated through 1 volt. And a coulomb times a volt is a joule. And so this is actually 1.6 times 10 to the minus 19 joules. Okay, so this is an energy unit. And if it says like a particle has 10 MeVs of energy, that would be its kinetic energy. That would be 1/2 mv squared. Okay, and then you will have a few questions where you're dealing with a parallel plate capacitor. So the same situation here. Now the capacitor doesn't have to be charged to be a capacitor. So this being a capacitor, if the distance between the plates is D and the area of the plates is A, then this parallel plate capacitor has a capacitance equal to epsilon naught A over D. So that's capacitance. And like I said, it doesn't matter whether the capacitor is charged or not. You go to the store, you buy a capacitor of a certain value, and then you bring it home and you charge it and use it however you want to. So this is just a function of the geometry of the capacitor. Now, when you do hook this up to a voltage, now it acquires charge Q, and the relationship, the Q is C times that voltage V. So the capacitor has the ability to store this charge, and Q is the charge it stores. Now, it also stores energy. So the potential energy, electric potential energy stored by a capacitor, your book calls it U, it's 1/2 CV squared, or 1/2 Q squared over C if you use this relationship, Q is CV. Okay, so this is the potential energy stored in a capacitor. And you know it's stored because if you pick up a charged capacitor, you're going to get a shock. And that's where the energy goes, is into your hand, stored in capacitor. Okay, I think that's all you're going to need for this chapter. There are some excellent videos that you should watch, and there's some excellent examples in the PowerPoint slides, and there are also lecture videos embedded in those PowerPoint slides.